Hi everyone, thanks for coming here. I know there was like a really interesting talk on the other track upstairs. It's way cooler there, so thanks for all your coming here. Today we're going to talk about the interface between crowd simulation and animation. It's a really, really deep topic, and we're going to just cover the things that we have figured out so far. And a bit about myself. This is me on my favorite pastime. I'm building a house here, even though in this picture it looks like a spaceship. That's how you do insulation these days. And some of you might know me as the author of Recast and Detour. I'm currently working at Unity. And me and my team, we are building tools to create believable characters. And our scope is more or less trying to figure out how to make the characters to move, when it comes to like the pathfinding, locomotion, crowd simulation to animation. And at the same time as making them perform stationary behaviors. We call them actions and locomotion. That's the scope we're currently trying to solve. It's a two-man team, and we know that there's lots and lots to cover. And one of our key criteria when we're trying to build these systems is that we want to support teams of all different sizes. It means that the indie developers with two guys working in their bedroom, they don't have the budget to have like thousands or hundreds of animations, have a technical director to put those all together, or a technical animator, and then do all the rounds and polishing that you need to have this triple A quality locomotion animations. So we try to basically work with a pretty small set of animations, and we try to make all the different steps to create these animation sets understandable. And one of our hopes are that this will also scale to more assets, like to bigger teams, and if you have more time to spend on the system, you will eventually get better animations out of it. And this kind of ties up to my earlier stuff as well. I've been talking maybe it was like 4 years ago about navigation loop, and so this will be sort of the structure of things we're going to talk today. And so it will basically cover everything from kind of pathfinding to steering, avoidance, animation, and this fix-up thing, which is the really specific thing about the navigation loop. So let's get started with the really basic thing. So in order to get the characters to move around in the world, you first need to do global pathfinding, or usually you want to do that. In case of navigation meshes, like we're using in Unity, it's going to be a list of polygons you need to follow to get to the goal. And I call this a corridor, like the list of polygons. And then on each frame, the first thing we do, we're going to look up the corridor and see where the next visible corner is, or where the path actually turns into be invisible. And that's going to be our desired direction where we're going to move to in this frame. And from that, and from the maximum speed of the character, we will get a desired velocity. That's where we want to move in this simulation step. And in steering, you might also want to do things like orient the character. Like in our case, it would be just trying to make the character face towards the desired velocity, for example. And next up is avoidance. So when you have multiple characters in the world, if you don't want them to go through each other, you need to do some kind of avoidance. Predictive avoidance, that's far better. So the basic idea is that if there's someone blocking you, we want to find a new velocity which will lead us towards the desired direction, and at the same time lead to as few collisions as possible. It's not always possible to find the non-colliding phase, but we want to slow down or speed up in order to avoid the other characters. And there are multiple ways to basically accomplish this avoidance. We are using something called sampled RVOs, or reciprocal velocity obstacles. The basic idea of velocity obstacles is that if you have someone in ahead of you want to avoid, you either have to choose left or right to basically find a path which doesn't collide with the other character. And this will basically mean that the disk of other character becomes a cone-shaped obstacle in velocity space. So as long as you pick a velocity which isn't inside this cone, it will lead to no collisions. And the obstacles we have in the velocity space are basically the boundaries of the navigation data, navigation mesh, and other moving characters in the scene. So we don't try to, for example, to choose a velocity which will lead us to a wall. And if you have, if the other characters are moving, these cones are moving in the velocity space, but the same thing still applies, that you want to find a new velocity which is outside of these velocity cones. Then if you have multiple characters, it still kind of builds on that same idea. You want to find a velocity which is outside of all the obstacle cones in the velocity space. And the reciprocal here means basically that we make an assumption that if you're avoiding someone else, the other one is also avoiding us. And this will basically make sure that there are a couple of corner cases where you might avoid too much, and it kind of results in decision flickering. So the reciprocal thing kind of helps with that sort of things. And we are using the sampling. And sampling essentially means that we have a certain set of velocity samples. In this case, this example, they are distributed as a grid in the velocity space. And then the dotted circle is the maximum speed of the character, or maximum velocity of the character at any given time. And then for each of these velocity samples, we will check what is going to be the time of collision within other agents. So it's basically moving circle against moving circle test. And that's going to be one of our weights. And then other weight could be, for example, the distance to the desired velocity. So that utility function basically allows us to find the velocity which is basically leading us towards our goal, and at the same time trying to avoid other characters. My coworker called this apples and oranges mixing. So it's going to be kind of tutti frutti weighting thing when you have they don't always have the same meaning. But with little testing and tweaking, you usually find a good combination of how to create a nice looking characters where they basically be able to choose how kind of aggressive they are towards getting to the goal versus avoiding other characters. But it's a tweaking thing and a fudging thing. And other popular way to do this is called ORCA, or I think it stands for Optimal Reciprocal Collision Avoidance. And the way it kind of handles this problem is that it represents every obstacle as a half space. And then when you combine this half space, it will result a convex shape in the velocity space. And as long as you pick a velocity within that area, it will lead to no collisions. So it's really conservative on what kind of velocities it allows, but it's really fast. So if you want to have, if you have big open areas and you have a lot of characters, this might be the best way to do that. It has some troubles in tight corridors and that sort of things because it's so, it basically sometimes rules out good velocities. But I think these are the usual two methods that you see people using. And there are a bunch of others, like every single year there's a new formulation of the topic. And it's really interesting to see that how they're moving towards sort of almost like how the human psychology works, or how we spend the least amount of energy to steer around other characters. But this is how we get the new velocity for the next frame. And now we're just going to skip the animation step, and we just making robot characters, RD2Ds moving in the world. And the final fix-up step in the navigation loop, it basically makes sure that once we figure out the movement delta for this frame, after that we will fix up the path corridor, which means that we can have quite a bit of slack in the steering, avoidance, and animation. It doesn't have to follow an exact path. As long as it's moving towards the overall direction of the goal, it will eventually maybe get there. There's a fair chance that it will happen, unless it gets stuck, of course, but then this becomes almost more like a probabilistic thing. But the fix-up basically makes sure that the representation we use for figuring out the optimal or the desired direction, it will be complete on the next frame. So here, for example, instead of going directly towards the next corner, this character actually took a sidestep, and we will add one extra polygon in the beginning of the corridor. Or if you're moving forward, you will take away one polygon. But this is really nice formulation for that we don't actually store the linear path. We always just basically in every frame we figure out the next corner. This is pretty quick to do. And in the fix-up phase, we make sure that we always have a valid path corridor leading to the goal. So we talk about the orientation of the character, and we talk about the velocity of the character. So if you think about like the bare minimum set of parameters we need to feed into the animation, assuming that characters are moving on a flat ground, it's basically the change in your orientation in this frame, basically the phasing of the character, and the speed and direction where the character is moving. Or you could think it as a velocity. Those are just like a different way of representing it. And depending on how you set up your animations, you may want to use a movement speed and movement direction, or the velocity. And at Unity, the way we are actually boiling this down is that we are using 2D animation blends. And 2D animation blends is basically that like all of those blue diamonds, they represent animation with a certain parameters. For example, it would be that the diamond at the top, it could represent a forward moving animation. The diamond at the bottom could be backwards moving, and the sides would be moving in different directions towards the sides. And when we try to figure out an animation with the parameters which are somewhere in between, we will figure out the neighboring animations, and then we will figure out in which kind of weight we need to blend them to get the resulting movement from our simulation to actually get the final result. But there's one small problem here. We have 2D blends, and the reason we want to use, in theory we could use 3D blends as well, but what we noticed in practice is that 3D blends are really, really hard for people to create. They are really hard to debug. They are even harder to visualize, like how that point cloudy thingy there happens, and what happens if you have a cross section. How would you add one extra animation there to make it even better? So for that reason, and for the sake of democracy, as we call it, we want to have it in 2D, because that's an understandable domain for less technical people, and it's also something that it's nice and easy to visualize. But it kind of means that we need to drop one of the parameters from the simulation to get some movement going on. A common way, what I've seen so far, is that you use the turning rate of the character and the current speed to do the parameterization. That way you get these nice curvy motions, and that's probably the de facto way of doing things. But we want to try, of course, something different. You know, like we know that this thing works, and there are certain shortcomings with it. So instead, we try to see what happens if we actually use the velocity directly, and just throw away the angular turning thing, and do that procedurally, which kind of means it's just rotate the character in the simplest case. And it works surprisingly well. And the thing that so basically this, the thing that you lose from using the angle and the movement speeds is that you can't have any sidestepping for the character at all, unless you have like two different blend trees where you switch between strafing and moving animations. So I'm going to next show how this looks in Mechanim. So here we have a simple blend tree. As I move the red dots, which is basically the values I feed from the simulation, I will get these different kind of movements on different directions. So one thing to note here, which is I found, especially with animators, which is controversial, is that we have this jogging on place in the middle, and we've been really, really sort of. It might be a bit too like happy how it's changing there, but we find it's really important to cover the whole parameter space. Like if you start to have holes in there, it becomes you need to fudge them at some point either in the simulation, or you need to. Usually it just happens that use foot slide, or the character moves sideways, or that sort of things. So that's one thing we are pressing to when we're working with our animators, is that you need to have that thing that's walking on spot, and they're like, nah, we don't want the character to do that. But I think it's the right thing to do. That if you start to see too much characters running on spot, then you need to figure out how to create like the higher level behavior, which is deciding whether we are standing, or whether we are walking, or whether we are running around. So definitely we want to do this kind of separation of different styles, and it's almost like people always talk about in programming separation of constraints. Here we want to separate the different styles of movement. And also, one thing about these curving animations versus using velocity. This was something that we were discussing that why we would like to use this new thing versus the old one. And then it kind of, at some point I just realized that, okay, so we're actually talking about holonomic versus non-holonomic movement. And all the simulation code for velocity obstacles and so forth, more or less everything assumes that you have holonomic movement. It means that the character can, at any given time in the simulation, they can move in any direction. For example, they might take a small side step when they're avoiding other characters. But if you're parameterizing your animations based on turning rate and the speed, then you're basically creating a unicycle. And this is non-holonomic. And then you're mixing apples and oranges again, that the simulation assumes holonomic, but then your actually animation representation is different. And might actually seeing that you're using still the same 3 parameters, the orientation and the velocity, or the movement direction and movement speed. But actually the orientation now has a different meaning as well. It actually is the direction where you're moving as well. So you're kind of combining, in a way, those 2 things. And if it's not represented in the steering and avoidance code, you usually get really funky looking movements at this point, and you need to do fudging again. And by fudging, I usually mean that you're going to do low-pass filtering, which means that you're going to hide lots of bugs in your simulation code. That's like the one thing I try to basically say with all these different steps is that I want to get to the point where none of the things in our navigation loop thing has low-pass filtering on it. It might result like robotic animation, but it means that we can turn on the low-pass filtering where we want to do that. But there are certain methods where it's almost impossible to get it working nicely without the low-pass filtering. So, of course, like this is time you'll be ready for. Like, how does it actually look like? I'm really scared because I don't see any. Like, I see only problems on these animations. I think it kind of looks okay. It's like if you think about AAA, and it's not AAA yet. But I think like for the sake of like, if looking at individual characters, I don't think this doesn't stand the quality we want to get. But I'm really happy how it actually turns out that we are now able to cover the whole set, and we have meaningful values on every single thing. And we definitely want to get this looking far, far better, but this is a good starting point. And this guy actually is like 3D scan person, one of our evangelists, Carl. I wanted to have like a nice looking character there. No more spiky hairs and short fielding guys. Also, a couple of things we do on top of this. So the turning is procedural. We're using a blending pivot point from mechaning. It's almost like when you're on your left foot, the pivot on the left foot, and when you're transitioning, it's basically almost the center of the mass. So we are using that for turning the characters, so we can get away a little bit of the foot sliding that you have in the turns, because we are just doing it. And also we are using Locomotion to make the character to pay attention a bit more where he wants to go. I think like in this example, it doesn't show much. It looks a bit worse when it's turning on, that off. But I want to make it more pronounced in the future to make sure that we can direct the attention of the character better. And here's 5 Carls, some of them jogging, some of them not. One of my litmus tests are, or actually 2 of them, is that I have this level where I have these corridors where there's just wide enough for 2 characters to pass through. And I try to watch like how horrible the behavior gets there. And the second thing is that as soon as you actually start kind of thinking about their behavior and not their animation, I think that's sort of like the low bar of the quality of the locomotion animations. Like here, like that dude there just walking and not letting that jogging guy ahead. Like I wish I had like this, I could model the frustration of the guy behind, like, shouting like, "Go on, Carl!" But that's the kind of thing that you're looking now, I hope so, is that instead of looking at the individual animation, you start looking at the kind of the microscopic behaviors between the characters. And that's definitely something that we need to look into. But I think like that once you get the animation to the point that it doesn't look completely horrible, I think that's a really good starting point. And here's like 30 agents doing things. there are a couple of spots there we will see that modeling the frustration would also help the overall behavior, would make it more dramatic as well. But at this scale, like if you have, especially in the more open areas, I think it's a nice model for having just the 7 animations and a good, nice-looking behavior for all the characters. And there are no dead spots, and they will do their best not to slide around and things like that. And you definitely start to see some simulation artifacts here, because you have so many people, you start seeing how they flow and that sort of things. So we have now looked at the whole sort of pipeline, how animation could fit in the navigation loop. We started with the pathfinding, figuring out the corridor, doing steering, moving towards the next corner in the path, doing avoidance, figuring out the orientation of the character as well, doing the animation, and from animation we get the movement. So this is sort of like root motion-driven locomotion, if you want to do it speak it that way. And finally, we do to fix up the corridor, so we are ready to do the next iteration. And but we wanted to do much better, of course. I've been really careful trying to use 2D animation blend and not parameterized motions, because we don't currently, in Mechanim, we don't have parameterized motions. And I think that's one of the key things to do next, is to figure out like how we can, we've been doing some prototypes where we had like a 2D grid on top of the blend space, and over time try to minimize the error for each of these samples and use it like a lookup table to fix up the values we pass into Mechanim. Because I think it's like, in order to get rid of the final low-pass filtering in this loop, which is the sum of the parameters, velocity parameters we pass from avoidance to animation. In order to fix the final thing there, we need to be more accurate how we present the animations to the rest of the system. And not just the parameterizations. I think there was a good paper, I think, or talk 4 years ago called Parametric Character Animation in Crysis 2, where they talk about how they did their parameterization. And, but the core idea is that when you ask for a certain velocity in a certain direction, you will get that kind of motion over that small period of time. That when you basically read it back, it will be within 5–10% of your requested speed. We also did this kind of, to understand better how this thing works, we did this little prototype. So what you see at the bottom is basically the grids where we're sampling, I think it's 15 by 15 samples. And for every sample, we see that what are the actual values returned by the Mechanim system when the different animations are being blended to create the final animation. We don't have extrapolation. We're not using extrapolation here. So what you can see you can see the shape of the convex hull of all the animation samples we have there. And that's definitely something we actually would like to pass back to the steering and avoidance. Like if we cannot represent those movements using the animation, we should definitely make sure that the systems below know that as well. Another thing we looked at everyone who has worked on the strafe sets, they know that there's always going to be feed crossing on when you go into the sides. So those 2 triangles at the bottom and the bottom layer, those are basically the times where you started having, when you have feet crossing or going through each other. So that's something also we could pass back to the steering and the avoidance as well, like try to avoid those spots because they will create your bad animations. But going in further, actually what is interesting is that if you look at the clouds, that going up is time, those constraints are quite temporal. Like they happen at certain points in time where you have left or right foot down. And if you look at even more closely, well, they are triangle shaped like this, which kind of implies to me that there are velocity obstacles there. And that would be really cool to actually put those constraints, temporal constraints on the avoidance code. So we try to avoid our own feet as we're moving in a certain direction. And it sounds stupid, but I'm certainly sure that actually happens when you're moving around in the world as well, for yourself as well. So this is the kind of thing we've been doing. Actually, yeah, one more thing about the rectangles on the ground. That the bigger the rectangle is, the more change there was in speed in a certain direction. over the course of the animation clip. So if you look at the animations which are going towards your back, they actually have much more fluctuation in speed. And that's also something that I would be interested to also push back to the avoidance and then steering. In this kind of case where the running or walking is pretty kind of standard and almost robotic, because that's probably what the actor tried to do. They don't fluctuate too much, but if you have like a limping animation or if you have a zombie moving around, they might actually have much more fluctuation in the speed of the character. So taking all this and turning it basically, this would be the movement style of the character. So they're basically the velocity constraint over time of your animation, as well as the feet, like how they're blocking your movement. And as we combine the feet velocity obstacle with this turning, which is trying to kind of conserve your pinpoint using this mechanic pivot, I think like that's a really interesting thing that I definitely want to try out in the future. For this presentation, I wasn't able to bridge the gap yet, but these are the things we're currently looking at. So to sum things up, we looked at how, so I think for us the big sort of things to understand from all these things so far was understanding the holodynamic nature of the character movement and what it actually means to move that into the animation thing as well.
Sorry.
No problem. And so that was something that I had to hunch when we started working on this stuff, that there's some reason why people want to use this curved motion, and usually that you get nice banking. But also, like I was always had trouble actually creating the code which would put nice banking, nice turning values into this animation system. And there was always cases where the character is facing a wall, and now what do what? And well, you end up with this that you have actually the starting animation transitions, and I think that's a really good way to dress up the starting and stopping of the character movement. Even with this hour system, I think that's something that if you have the time and the people to do that, that definitely kind of improves it kind of spoils the responsiveness of the character early on, but it basically kind of, it looks far better. And the second thing that came out of this research and work was that understanding the constraints from animation that are meaningful to feed back to the rest of the system. I definitely think that the ownership of the movement has to go in one way. There can't be that you're using steering and avoidance, and then animation is doing stupid things, and then physics is doing stupid things on top of that, and then you run out of sync on this whole thing. So the whole point of the navigation loop is to do a step at a time where you can make sure that you're pushing the responsibility, basically kind of funneling the decisions down. So the animation, the only thing it needs to do is basically try to match the velocity that has been passed from up towards down. There are a couple of things like going even further, which we haven't started yet, is that we want to make a far better looking turning. Like, since it's procedural, we need to gather some data on how people are actually doing that in practice. Like, you could see on certain corners there, they were doing way too quick turns, and sometimes they're way too slow. And I haven't quite figured out yet, like, what's kind of the underlying concept, like why Ben knows, you can tell. But I would like to be able to take some of that data and apply that to the turning, so it feels far better. Now it's lerping with fudge vectors kind of thing. It kind of works well. The gameplay programmers version. And go even further, I would like to understand how the center of the mass should behave with these characters. I think that's the most important thing. Like a few years ago, there was Ken Perling talking here, and we talk about character animation. He wanted to do like a full procedural character animation, and his basic thesis was that the body is basically just a vessel moving our head around. And I think there's some kind of wisdom in there that I would like to be able to kind of pull back here. So the actual things we would simulate would be the position and orientation of the character, position and orientation of the upper body, because that's how you act, that's how you pay attention, head as well, and then try to figure out how we can also measure and simulate the center of the mass of the character, maybe upper body. I don't know exactly where the center of the mass is. Maybe it's a gut thing. and then also have that as part of the steering and avoidance. I'm sure that it shouldn't be too constraining how we do that, but it might actually affect how we think about changing our speed to a certain direction or things like that. So that's all I had to say. Now I think there's time for questions.
Hey.
Hi.
I would be curious about, let's say, your velocity changes drastically from one frame to the next, where a plant and turn animation would look the most natural. How would you go about this? I mean, let's say your parametric space currently does not cover the velocity that the desired velocity, and you would need a special animation like, let's say, a plant and turn. How would you go about implementing this or integrate this into this loop?
So currently our dynamic model is set up so that if you have really drastic change in desired direction, it actually, over time, we have maximum acceleration change. So basically we would handle that using, there's no special reaction to that one, but it just basically, it means that you will move there a little and then over time move the different direction. But I think that's really important when it comes to acting, is that you want to somehow show sudden changes in behavior. And I think like that's maybe more interesting way of thinking about the problem. I know that a lot of people are using special kind of transition animations for that when you have sharp turns, and I think that's still definitely a viable solution. You run into these like foot syncing things again, but you know that's how locomotion is. But for the time being, we're just handling that using acceleration. And that's a cheap way, and then the expensive way is to figure out that when these things happen and to play the specific transition animation.
Hey, thanks. So I'm from a film background, so my question might be a little naive. But first of all, that's really cool how they were bunching up even without the frustration. I felt that was pretty compelling. When the cursor was behind the agent, though, I felt there was like kind of an unnatural acceleration. So I was thinking, all right, so we could ask an animator to fill in that cycle. Would that be just, if the relative velocity is behind you, you fill in that motion, would that be enough to correct that? Or is there something more going on?
I'm almost compelled to pass the microphone to Ben. He can maybe answer that next to you.
Sure. Go for it.
But I think that those errors are currently coming that we have really simple model for turning the characters facing. So generally it's facing towards the desired direction. And it means that if you're moving there, but you need to basically go across the character, it kind of tries to still facing where it wants to go, but taking side steps. When it's facing like 360 or 180, it actually means that I would like to have more anticipation on the upper body, and then I want to have better model on how these characters need to be turned. Currently, it's like a programmer art version of turning around, and I think...
so it's more than just filling in that space in the 2D grid.
That's right, okay. Yeah. That's basically that us trying to replicate the missing parameter. That's roughly how it works, yeah.
Yeah, no, I agree with Miko.
Yeah.
Okay. I was just wondering, so the animation, does that dictate the movement for that frame? So the output from the animation, is that dictating the movement for the frame? And are you actually running a character controller after that, if you see what I mean, in order to prevent any sort of potential failures in the system, if you see what I mean?
Yeah. So yes, in our case, the animation is driving the final movement, but there might be different kind of errors, as I explained, from steering. You might actually steer a bit to the left, to get the more curvy motion or things like that. The avoidance can, take a side step from the desired path as well as the animation has some fluctuation in speed and whatnot. Or in our case, we cannot currently represent like exact movement the simulation system is passing in. So all those things will be basically fixed up by the fix-up thing in the end. So it can basically, if it wanted to move over here, but it took a side step, the fix-up phase will make sure that you still have like a nice plan for the next frame for movement. So it can go quite far. Then the further you go from this kind of cone, the more eventually the consistency will be matched. So as long as you're moving directly to the next corner, that will be the fastest path to the goal. But if you need to deviate, it will basically be more eventual. And if you have basically really wonky direct model, like you have really low acceleration, which means that you might not ever make a certain tight spots in the level. For example, while I was fine-tuning that case where you have all characters were funneling into the one spot, my acceleration was really slow, so it was almost like a pendulum going there, trying to get to the point, but not quite reaching it. So if there's lots of error in the loop, then it might not make it. But the whole thing tries to keep the plan always valid. That's the thing.
Thanks. Yeah, I just had a question about the predictive avoidance. Mm-hmm. So does that incorporate the static collision as well as your moving objects, or is it purely the moving stuff? And once you've got past that stage and you get to the fix-up, does that potentially result in new pathfinding? So you might have been pushed off your path and you need to get back. Is that how that works?
So it contains both the wall segments of the navigation mesh, which means that things where the character cannot move. So if you have like a character next to a wall, it tries to take over from the right. It tries to go to the left instead. So basically it tries to cover all the things that you could, all the velocities that you can basically choose in this frame, or they're being blocked. Again, the second question I can't remember, but basically it was that if it's deviates from the path, if it deviates a lot, then we will do replan. We actually do replan every now and then. But in general, the fix-up phase, what it does is that it's almost like a rubber band. So if you move the character around, we will do, since the delta distance is really small every single frame, we can actually change the path corridor, like the polygons that are leading to the end. So if you're moving forward, we will take away one polygon, so it will shrink. But if you're moving backwards, like away from it, we will add new polygons there. So that way we can keep the plan solid every single frame, even if the characters are doing. Yeah.
So I was wondering whether or not you believe that if you extend what you're doing, whether or not you'll ever be able to get really truly believable motion using this paradigm of character control, entity-driven movement, and then trying to work out what animations to play to fulfill it, or whether or not you think that eventually then there'll have to be some other kind of paradigm which maybe does something very different.
I think this one will help us a bit, but I think like things which are more based on IK and simulation, like as a programmer, I would love to find a way where we just do everything procedurally, because it would make everything easier. But I think for the sake of artist control and kind of the expression of the people, of the creative minds, I think we need to have some animation clip there, or some way of them expressing what they actually want to see. I've been really excited about the Bungie guys, how they sort of like used kind of IK as animation compression and those things. So we're looking into those things as well, to try to see that what other possibilities there would be. But I think it's big and messy, complicated thing there, and starting with something that people know already, how to author animations. I think that's also one of those democratic goals we have. It's basically trying to make as little mental change as possible, but still try to make the whole system more robust and believable. Mike Kohlberg always talks about he wants to do procedural character animation. Yeah, me too. But you have to be real.
I think everything's clear. Thanks, Mikko.
Thank you.